So now we're at one of the most interesting parts of this process. We want to try to figure out a closed formula for d sub n. That's the sum of the c sub n sequence. I went ahead and put in a few more entries in the table because I think that's going to make it easier to guess or to answer a couple of the first questions, to kind of address some of the first few hints. So I took it down to n equals 12. And let's look at the first hint that I give. In case I mean, it's really good to try to just think about what could, even if you couldn't come up with the formula, what could you say about those numbers as well? Let me give you one more flash of that since it's not on your PDF. And you can obviously do that, generate these yourselves or even go further, which is not a bad idea. I should have put that in as another hint. Just go further sometimes is a good idea. So let's look at the hint number one. Whenever you've got a sequence, it's really good to just approximately look at what it does. Does it get smaller? Does it get bigger? Is it always positive? Is it always negative? Does it alternate? If it does get bigger, how does it grow? And so let's look at the growth rate of this thing. Well, and let's compare all the growth rates. Well, a sub n doesn't grow at all. B sub n grows linearly. If you graphed these guys, they would just be a straight line. If you graph the function, this is just y equals x, basically. It's exactly the most simple linear function. C sub n, let's see, does that grow linearly? Well, here it grows by 2, by 3, by 4, by 5, by 6. Oh yeah, of course it does, because that's what we're adding each time. So in other words, the growth rate is not constant. And of course, we already also know that from the closed formula. It's roughly a quadratic. If you look at that and you just ignore the lower order terms, you get, and we just think of it as like sort of y equals x. Let me write it out just with different letters because sometimes that activates our function intuition better. That's approximately equal to just x squared over 2. When x is big, x minus 1 is pretty close to x. So especially once you get past the first few terms, it's really a pretty simple function and it should look quadratic. Let's test that. Even if we didn't know that, we could see that, or we can verify it once we do know it. Like, let's look at what happens, for example, when you look at n equals 4, you get 6 for Cn. So notice I'm not even analyzing Dn yet. I'm looking at the other cases first. When n equals 4, Cn is 6. So let's try doubling n. If it's a quadratic, doubling x or doubling the input should quadruple the output. Okay, you get 28. Well, that's roughly 4 times 6. It's not exactly by any means, but it's roughly. Okay, let's try a few other examples. When n equals 5, C sub n is 10. When n equals 10, and this is where it's really helpful to get a little further than what I had you do before, you get 45. Okay, 4 times 10 would be 40, 45. It's in the ballpark. 6 gives you 15, and 12, you double the input, 66 is pretty close, roughly, to 4 times 15. So that's confirming that this is roughly growing quadratically. When you double the input, you roughly quadruple the output. Well, that's a really good test to apply to d sub n. Maybe it's also quadratic, and that would give us a hint as to maybe the general shape of the formula. Okay, so okay, one thing to notice also is that when you look at the first few terms are going to be a little misleading because that n minus 1, that minus 1 is going to have a bigger impact. It's not going to fit the pattern very well. So for example, n equals 2, C sub n is 1, n equals 4, C sub n is 6. That's significantly more than 4 times. So let's just drop the first few terms. But again, let's say 5 gets you 10 on d sub n, and 10 gets you 120. Okay, that's a lot bigger than 40. A lot bigger. So it's much more than quadrupled. 6 gets you 20. 12 gets you 220. That's times 11. Again, much bigger than times 4. So what this is doing, this is growing, it does indicate this is growing faster than quadratically. Okay. So we've got something that grows not at all, or we could even write that as like an n to the 0, suggestively. This is an n to the 1, and then this is quadratic growth. You might want to pause it right now. What do you think might be here? Maybe a cubic function. Maybe something like something involving an n cubed. Okay. Now, is it exactly n cubed? Oh, heck no. N cubed here would be, 10 cubed would be 1,000. Okay, just like here, this isn't n squared, but it's close to n squared over 2. Okay, 12 cubed, ooh, what is 12 cubed anyway? Let's see. 12 cubed, 1728. Okay, this is nowhere close to 1728, so if it is a cubic, it'd be a cubic divided by something. Okay, but that's not surprising because this was divided by 2. Okay, so we've got a good start here. All right. Um, good time to pause and see if you can think. Okay, so and now I think the thing to do is to see, boy, these should really make their own pattern. If they, since it's such a simple process, I'm just repeated summing, repeated summing, repeated summing. There should be a pattern in this sequence as well. That these formulas are going to get probably more complicated, they're going to grow faster, but there should be some similarities among them. So that's a good place to stop and see if you can come up with a guess for this term. Okay, but if you don't want to do that, let's keep going. My next hint, yeah, so that was hint 2. Look for the pattern in the closed formulas. Still pretty challenging to do it. And now this is a really big hint. Okay, calculate the ratio of dn over cn. Okay. So what we're going to do is it's really taking that previous hint really seriously. What happens if you compare these numbers to these numbers and try to express these guys as this modified in some way? And we should also look at the same thing if I look at b sub n over a sub n or c sub n over b sub n. Okay. So in fact, let me just fudge this table just a little bit. B sub n over c over actually b sub n over a sub n is really easy because it's just b sub n. So that's just n. C sub n over b sub n. Okay. Well, here it doesn't really make a lot of sense, 0 over 0, but we know that those kinds are kind of weird. So that's going to be 0. Okay. 1 half. 1. 6 fourths reduces to 3 halves. 10 fifths reduces to 2. 15 6, if you do it out, reduces to 5 halves. 21 over 7 divided by it reduces to 3. 28 over 8 is 7 halves if you reduce it. 36 over 9 is 4. And this is 9 halves. And I'm going to rewrite these guys. And whenever you're looking at doing inductive mathematics, you want to write things to emphasize the patterns. So this is a good example. I'm writing these things in a way that might seem a little perverse, but makes the pattern much clearer. Okay. 11 over 2. Okay. Now, of course, we could have derived that. We're still not analyzing d sub n directly. We're looking at c and b, which we already have a very good handle on. We could have derived that just by saying, oh, this divided by this, the n just cancels, and I get n minus 1 over 2. Oh, yeah, okay, 11 over 2. Yeah, that's n minus 1. 10 over 2, 9 over 2. Oh, yeah, totally. Okay. But notice we got it. We could see the clear pattern just by doing a few examples, and it's pretty obvious what the pattern is, and we can be pretty confident that it's going to continue. And of course, we're going to prove that with mathematical induction pretty soon. Okay, so now let's do it for d sub n over c sub n. Okay, and then the first few don't really matter. Okay, 0. Okay, 1/3. 4/6 is 2/3. 10 tenths is 1, but you know what? I bet it's a good idea to write that as 3/3. 20 over 15 is 4/3. Hey, we got something. That's 5/3. 56 over 28 is 2 or 6/3. If you reduce these all out, 7/3. 120 over 45, you have to think about it a minute, but that's 8/3. 165 over 55 is exactly 3 or 9/3. 10/3. Ha. Okay. So let's see. So the pattern was n minus 1 over 2 for the ratio, and that's why you take this guy and you multiply it by n minus 1 over 2 to get this guy. Now we're looking at what do we have to multiply this thing by in order to get our mystery numbers. Okay, and that's looking like, you might want to pause it, but it's not too hard. Now it's n minus 2. Notice the n was 12 and this is 10, 11, that corresponds to 9 over 3. Okay. Now I'm not saying that these numbers are n minus 2 over 3. But what I'm saying is that the ratio of these guys to this one, and that's where we know a formula, is n minus 2 over 3. So now we've got it. N minus 1, n minus 2 over 3 times 2. And let me over-decorate things even a little bit. Ooh, you know what? This one doesn't seem to be a fraction, but you know what? I can totally write it as a fraction. N over 1. N times n minus 1 over 2. You know what? I'm going to write that as a 2 times 1. I'm going to write this as a 3 times 2 times 1. Oh, okay. This is looking very interesting. This bottom is a very famous function. That's the factorial function, at least so far. And on the top, now I think with 3 examples like this, or well, kind of 4 with this really simple example, but 3 examples that look very similar now, that's usually enough to start generalizing to the rest of the table. Okay, so I'm going to change this back to E sub n and F sub n. Oh, but I think it's a good place to stop the video. It's a little long already. So we've got a formula now for, a closed formula for the sum of the sum of the sum of ones.